So if you can come at 3 p.m., A, yes, or B, no. All right, let's try 1 p.m. A, yes, B, no. All right, looks like about half of you can't come at any one of those times. So I'm just going to pick 2 p.m. That sort of works for me. It's more convenient. I'll record the help session and I'll place it online, but we will have a help session on Tuesday at 2 p.m. If you can make it, that's great. If you can't make it, that's fine. Like I said, I'll record it, so there won't be anything that's, secret or whatever that goes on in that help session. I'm not going to hand out a copy of the test, but we will talk about the test and sort of how to prepare for it. So I'll post that online. Likely it'll be in this room, but I'll send you a message and let you know. I have to see if this room is available. So we'll do Tuesday at 2 p.m. Tuesday at 2 p.m. and I'll send out a notice on Moodle for y'all. Okay. All right. Let's do a few problems here. We're going to start introducing friction today. I don't think we've had friction yet, but on the test you will have friction on your problems, or at least on one of the problems. Remember, you'll probably have either one or two projectile motion problems. You might have a separate vector problem, and then you'll have one or two Newton's laws problems. You'll have 4 problems total. All right, so one or two projectile motion, maybe one vectors problem, but I might work that in with a Newton's laws. The vectors are sort of inherent with most of the problems that we're working, and then one or two Newton's laws problem in two-dimensional problems. Now you will have one-dimensional problems on the multiple choice, but hopefully those are pretty simple now. At least one of those will include friction. When I talk about friction, we can talk about it in 2 different scenarios. You can think about friction in a macroscopic sense or a microscopic sense. All right. Macroscopic just means like if I have 2 surfaces that come together like this, these 2 surfaces are going to experience friction just simply because the crags and the crevices are all gonna catch on one another, and they'll just physically get, or they'll mechanically be obstructing the motion of the other. That's what you think of when you think of friction, that you have these surfaces that are just bumping up against one another. Right? And if you were to plot now the frictional force, which I'm going to use a script F, and the smoothness of a surface, what do you think would happen? Would the frictional force increase or decrease as the surfaces become more smooth? It's going to decrease, right? So it's going to look something like that. Your frictional force will decrease. But what they find is that as you decrease the, or as you increase the smoothness of these surfaces, eventually what you're going to get is that you'll find that the frictional force will actually turn back up again. Can anybody explain to me why we have this uptick in the frictional force? As you make a surface smoother and smoother, why do you get the frictional force actually begins to increase? That's right, because you get the molecules actually get closer to one another, and so you begin to have these intermolecular forces. There's also the fact that you just have a greater surface area that's in contact with one another and with each other, and so that increases the smoothness. But this illustrates the difference in these 2 regimes. As we consider this regime, we're talking about macroscopic friction, and as we're considering this regime, whereas you increase the smoothness, your frictional force increases, this is microscopic. So those are just sort of 2 different scenarios of friction. Now, friction is always opposite the direction of motion, or it's opposite the direction that you intend the motion to be, or that the object would tend to be. So for example, if I have an object and it's moving in this direction with a velocity, or we'll say that it's accelerating in this direction, then I have a certain force that's acting in this direction. The frictional force is opposite the direction of motion. the frictional force will be opposite the direction of motion. Or, let's imagine that I have an inclined plane, and I have an object that's sitting here, and it's sitting so that it's not moving at all. It's a static situation. The velocity is 0. What is the direction of the frictional force in this case? Is it up or down the inclined plane? It's going to be up, right? Because this object would tend to move down the inclined plane, so it's going to be opposite the direction that that object would tend to move. So my force is up in that direction. And by the way, the downward force is some component of the weight, Fw. Let's say that this angle is 30 degrees. This is going to be Fw cosine of 60. Hopefully on your inclined planes, as you're working through the homework, you're sort of past the point of actually writing out all the vectors, that you can just skip right ahead to where you label all the x and y components of the vectors, because you know the force weight is always going to be there. So if you're not to that point yet, that's fine, but you will want to be to the point where you can just look at an inclined plane and say, well, I know that the weight component is in this direction, the x component of the weight, the y component of the weight has this value and is in this direction. Y'all are to that point, maybe? Yes? No? Okay, you want to be at that point to look at an inclined plane and just say, boom, 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 I know what these forces are. We've done several of those, and we'll do a couple more, but some of that's just going to be sitting and looking at it on your own. All right, so we have two types of friction. We have static friction and kinetic friction. Static friction we're going to express in this way, Fs. We'll use a script F for frictional forces, and S subscript for static frictional forces is less than or equal to the coefficient of static friction times the normal force. And this static friction acts on objects that are stationary, are static, that are not moving. This mu s, this is the coefficient of static friction. You'll actually measure this in the lab next week, in the next lab after your midterm. The coefficient of static friction is measured experimentally. You just simply measure the static frictional force, you measure the normal force. When you measure these two, then you can find mu s is just equal to, the static frictional force divided by the normal force. All right, so that's our coefficient of static friction. We'll have a very similar thing for kinetic friction as well. Also want you to notice this inequality. Let me look at something. I want you to notice this inequality that we have here, that the static friction is less than or equal to mu s times Fn. I will sometimes write it not as that, but I'll write it as an equality. Fs is equal to mu s times the normal force. Really what I'm implying there is not that the static friction is equal to that, but that the maximum static friction is equal to that. Okay? Let me explain what I mean by that. I'm going to go down to the next slide. Usually I will write it in this way. I'll just leave off that inequality. What that means is that if you're pushing a block, or you're pushing like a big piece of furniture, all right, I push on it in this direction, say with a force equal to 10 newtons. And with a force equal to 10 newtons, the velocity is equal to 0. The acceleration is equal to 0, and the velocity is equal to 0. If there was no friction in this case, with this block, it would move in this direction with an acceleration given by Newton's second law. So I know that there is friction. What is the direction of the frictional force? Is it to the left or to the right? To the left, right, because this force is pushing in this direction, so the frictional force has to be the opposite direction. So my frictional force looks like that. Now, if it's not moving, if the acceleration is 0, then I know that the net force has to equal 0. That is to say that F minus Fs equals 0, so F is equal to Fs. So my static frictional force here is equal to 10 newtons. It's not moving of equilibrium of forces, so the static frictional force is 10 newtons. So imagine that this is that piece of furniture. I can push on it with 1 newton. That means that the static frictional force is what? 1 newton. I can push on it with 2 newtons, so the static frictional force is what? 2. And I can push it with 3, so the static friction will be 3, and on and on and on, until I get to that maximum frictional force that this thing can withstand. And once I reach that maximum, then it's going to start moving. All right, so that's where that inequality comes from, that our static frictional force is actually a range of values, and it depends on your situation. That if you're pushing on it with 1 newton, your static frictional force will be 1 newton. If you're pushing on it with 2 newtons and it still doesn't move, it's going to be 2 newtons all the way up to the maximum value. Usually we'll just be concerned, well, no, never mind. Let's nix that. We'll see how it comes up in problems in just a bit. All right, now kinetic friction acts on objects that are in motion. Um, kinetic friction is going to be Fk. It's going to be equal to mu k times the normal force. So remember, this is very similar to what we had for Fs. It's identical basically, except that the mu's are different. Uh, so the kinetic friction comes about when objects are in motion. So let's say that let's say that the maximum static friction for this thing is 10 newtons. So if I push on it with 5 newtons, not going to move. If I push on it with 8 newtons, not going to move. When I get it up to 10 newtons, as soon as I exceed 10 newtons, when I get to 10.001, then it's going to start moving, right? Because I've exceeded the force of static friction. And now, as it's moving, the force that becomes relevant is the kinetic frictional force. So if I have an object, let's say that Fs is equal to, that is Fs max, which again, I'm going to imply that. I'm going to write it here, but normally I won't write it. Let's say that Fs max is 10 newtons. If I push on it with 8 newtons, not moving. All right, if I push on it with 10.01 newtons, then it does move. And when I do that, the static friction is no longer relevant. Instead, what I get is the kinetic friction. So the kinetic friction is in play when it moves, when this object's in motion. Now, for almost all materials, the static friction is bigger than the kinetic friction. For almost all materials, the static friction is bigger than the kinetic friction. Uh, by the way, I want to sort of go ahead and nip this in the bud. We'll see this in a little bit later, but I want to go ahead and get you in the habit of thinking that kinetic friction is also like sliding friction. You'll see why when we get to this in just a bit. But you can think of it as sliding friction. So it's like the table slides across the floor. The two surfaces are moving with respect to one another. That is the surface of the legs on the bottom of the table and the floor. They're sliding with respect to one another. So that's kinetic friction. Whereas static friction is they're not sliding with respect to one another. So when you think about kinetic friction, I want you to think about sliding friction. That'll help you in some of the ways that we think about this. So there's a good application of this that you may or may not have witnessed before. It sort of depends. Like when I was a kid growing up, and my wife goes out to where we live. We lived way out in the country, right? And in the country, sort of traffic laws are a little bit different. Like my uncle, for example, he's sort of disabled in a way. He can live by himself and all that, but he was kicked in the head by a mule when he was a kid, and now he's just sort of, just not sort of quite right, developmentally disabled, as they would say. And so he drives around, but he doesn't have a driver's license. His truck doesn't have any inspection or anything like that. So anyway, traffic laws are a little bit null and void out in the country. And in a similar way, stop signs are sort of gentle reminders that you need to watch when you come through an intersection. Not so much that you need to stop. And my wife, she was sort of blown away by this. Because some stop signs you do stop at because you know like the log truck is going to come along and barrel through and not pretty. But other stop signs are just gentle reminders. So when you come to a stop sign, if you stop, as you do, you see a good application of kinetic versus coefficient versus static friction. So imagine this afternoon when you're leaving, as you're going up Maidwood or wherever you parked, and you come out to Highway 1, instead of just flying right through that stop sign, which is not a good idea to fly through that stop sign, right, because there's a lot of traffic. But even instead of just coming to a rolling stop, come to a complete stop and try this. What happens when you come to a complete stop at a stop sign to your car? Yeah, you sort of lurch forward a little bit and then you come back. The reason that you have that, as you come to a stop sign and you come to a stop, do it a slow stop, or I mean come to a complete stop but do it slowly, or even if you come to a quick stop you can usually feel it. You'll feel yourself lurch forward. That's because you're transitioning from one type of friction to another type of friction. Now inside your car you have these rotors and you have brake pads and they clamp down onto those rotors, and the rotors are turning when your wheels are turning, and when it comes to a stop the rotor stops turning, right, because those brake pads have stopped it. What type of friction are we transitioning from and to what type of friction as we move from moving to stopping? We're going from what type of friction to what? Kinetic to static, right. So when you have that transition from kinetic to static, you have this difference in the forces that cause this sort of lurch forward. So when you stop, the car lurches because frictional force transitions from static to or from kinetic to static. And almost always, always as far as we're concerned, the static frictional force is greater than the kinetic frictional force. And since there's that discontinuity, that's what causes that little lurch forward. We see this also with like heavy furniture, and you've probably witnessed this before. If I have a piece of heavy furniture and I want to push it across the floor, right? Uh, it's going to be easier to move after I get it started. You ever witnessed this with a big piece of heavy furniture? After you get it, it's really hard to get it moving, but once you get it moving, it's a lot easier. And that's because that static friction is bigger than the kinetic friction. So I want to point out, we'll work a problem here soon, a very simple problem. But remember that friction in general is equal to mu times the normal force. Just a quick little aside, and then we'll move on to a little problem. Notice that I can increase in friction by changing two things. I can either change the coefficient of friction. That's hard to change. The coefficient of friction would mean that I would have to actually change the materials. This is dependent upon the materials. Uh, you can find tables for the coefficient of friction. They're determined, as I said, experimentally. But for example, ice would have a bigger or smaller coefficient than rubber. Does ice have a bigger or smaller coefficient than rubber, for example? It's going to be smaller, right? Because ice is slicker. It has less friction. And it's not only dependent on the material, but it's actually dependent upon the two types of material. So when you see the coefficient of friction, or when I describe it to you in a problem, I'll provide it to you or you'll need to find it. It'll give the two materials. So like rubber on steel might have a different coefficient of friction than say wood on steel or whatever. So whenever you see the coefficient of friction, it's dependent upon the material, and not just one of the materials, but both materials. The other thing that you can change is the normal force. So back to this table, if I want to move this table, I can make it easier to move by putting those little foot pads on the bottom, right, that make it slide across the floor. That changes the coefficient of friction. I can make it more difficult to move by getting one or more of you to sit on top of the desk. And if I have more weight on the desk, that increases the normal force, and that makes it more difficult to move. You can try it too, like with your calculator or your clicker or whatever. If you have it on the desk and you push it across the desk, it's pretty easy. Right, y'all try that. Push it across the desk. Pretty easy. But then notice if you push down on it, it's a lot harder to push across the desk because you've increased the frictional force. You've increased the normal force, and then you increase the frictional force. Let's look at a really simple problem. I have this block. Force is pulling the block. The block is not moving. What is the maximum force F so that the block will remain stationary? So here I've already labeled all the vectors, all the force vectors. I want to, I can do my coordinate system here. You probably shouldn't really need to do this, but let's just go ahead and do it just for the sake of being thorough. My normal force is there. My weight is here. I have a force here. And then this is my Fs. I apply Newton's second law. I know that the sum of the forces in the y direction is MAY. The sum of the forces in the x direction is MAX. In this case, these are both stationary. So AY is equal to 0, AX is equal to 0. So the sums of these forces are both going to be 0. This is going to be Fn minus Fw equals 0. F minus Fs equals to 0. I'm looking for the maximum force F. So I want to know what F is, but I know that F is equal to Fs from this. And so I need to find Fs, but I know that my Fs max is equal to mu s times my normal force. So I need to find my normal force in order to figure out Fs. And once I find Fs, then I know what F is. So here my normal force is equal to the weight, which is equal to mg, which this was a 1 kilogram block, so this is equal to 10 newtons, 1 kilogram times 10 meters per second squared. So that is my normal force. Can take that, put it in here. 0.1 is mu. No units on the coefficient. It's just a ratio of two forces. So my static frictional force is 1 newton. That means that this is 1 newton, so F is also 1 newton. I know that was fast, but you know, y'all should really be at the point now. If you're not, really need to come see me or look back at the homework. But you should really be at the point here where you just look at this and I say, well, of course, these two forces are equal and these two forces are equal. So really all we're throwing in here is that our static friction, sort of just really a new formula, that our static friction is equal to mu s times the normal force. That it's just related to both those coefficient and the normal force. All right, let me just sort of summarize our equations heretofore, because we don't really have that many equations as we've had all the way up. Now we've got all the trig and stuff, and that's sort of all separate. Like I don't really count that as an equation. But really we just have, you know, our kinematics equations. X equals V naught T plus 1/2 AT squared. V is equal to V naught plus AT. We just have those two equations. Remember, we have special cases of those equations for projectile motion, where AX is equal to 0, AY is equal to 0. And so we can write those equations differently for projectile motion. In the x direction, I lose this term because AX is equal to 0. And so this sort of becomes a different equation where X is equal to VX times T. And then the Y equations look just like this, but with Y subscripts. And then we just have Newton's second law. The sum of the forces equals MA. And now we have these new things, that the static frictional force is equal to mu s times the normal force, and the kinetic frictional force is mu k times the normal force, Fn. Right, of course, as I said, really it's implied here that this is less than or equal to, but I'm not going to write it as an inequality. I'll just write it as an equality. Okay, that's really all there is. But as you know on the test, it's not really about the formulae. Like anybody can memorize the formulas. No one had to apply them, and that's really the hard part. All right, let's try working this problem. This is from an old test question. You will have a two-body problem. You also will have a an inclined plane problem. Uh, you could have those separately. The inclined plane will have two bodies on it, and you can see some different examples like that in the old test, and we'll work some, maybe not today, but next time. Um, but you could also have a two-body problem like this next one, where it's a 2D problem. You have forces in two dimensions, um, but you also have the thinking. You have forces in two dimensions, but not on an inclined plane, and that's what we have here. Um, all right, so here where I have two bodies, what I want to do is treat the two bodies separately and draw all the forces that act on the individual bodies. So here I have block B and I have block A. They're connected by strings. We can sort of think that they're connected by these rigid rods, if you will, because they don't change shape, if you will. Uh, let's see. Oh, and this is all static. Yeah, so it's not moving at all, so we can just assume that it's that the angle remains constant. I can start labeling my forces. I have block B has a weight of 20 newtons. I know that it also has a normal force. I'll call this FNB. You should already look at this and say, well, I know that the normal force here, because this is, you know, on a horizontal plane, that the normal force will equal to the weight. You should be able to look at this, right? Y'all can see that the normal force is equal to the weight. All right, I have a couple more forces. What are the other forces that are acting on on the block B? We have the frictional force. What is it? Which direction is it in? To the left or the right, the frictional force? It's going to be to the left, right? So I have, I'm going to call this Fs. There is no frictional force on A, so I'll just call it Fs. And then I have one other force, which is what? I have tension. So I have this rope, which is pulling on this block. And I'm going to call this Ft1. Now, at this other, we're going to have a second body, but actually, we're not going to treat block A. We're actually going to have our body right here, because I have forces that all act at that point. All right. So what are the forces that I have acting at this point? I have three ropes, right? So I have three different tensions. So I have a tension that comes up here. Let's see, and I call this Ft2. And then I also have this tension. I'm going to call this, though, not Ft2, but I'll call this Fwa. Because it's like that block is just hanging there. And so whatever tension is in that rope is given by that block A. I have a third force, right? I have a third force that acts in this direction. This force is going to be what? The force that acts in that direction will be what? It's going to be what? Yeah, you're getting a little bit of, who said that? The friction. Who said friction? That's right, it is going to be our frictional force. We're getting a little bit ahead of us. This is actually going to be Ft1. And then we will see later that it will be equal to the frictional force. Okay? This is going back to Newton's third law. Remember, every force has an equal and opposite force. This tension here that's acting in this direction is also going to act in this direction. It's like if I were to tie a rope to the door there and pull on it with a force of 100 newtons, I'd be applying 100 newtons in this direction. The force would be also, the door would also be applying 100 newtons in the opposite direction. It's Newton's third law. Anytime I'm applying a tension on one end of a rope, I get that same tension on the other end. All right, so here I have two bodies. I can apply Newton's second law for both of them. I'll do block B first. I can say the sum of the forces in the x direction is going to be Ft1 minus Fs. This is going to equal 0. The sum of the forces in the y direction is going to be Fnb minus 20. I'm going to call this Fwb. You can put a number if you want, but I'm going to keep it at Fwb. and that's equal to 0 as well. Those are pretty simple. Um, I can go ahead and solve for some of these things. I know that FNB now is equal to FWB, which is equal to 20 newtons. So that's my normal force. I can also say that Fs is mu s times the normal force. That's going to be 0.2 times the normal force, which is 20 newtons. 0.2 times 20 is 4 newtons. All right. Now for block A, it's going to be a little bit more complicated, but I want you to do this on your own for a few minutes. For block A, the first thing that I want you to do is you draw your coordinate system and resolve those vectors, because you have one vector here that is unresolved, and we need to resolve that vector into its x and y components, and then we do our sum of the forces in the x direction and our sum of the forces in the y direction, and you'll get a similar set of equations. So let's go ahead and do that. Just resolve your vectors onto the x and y components, because you have that ft2, and then write out our Newton's second law, applying Newton's second law to that body for block A. What's my y component of ft2? Where I'm going to do the sine of my angle was 30 degrees. And then the x component, of course, is going to be cosine. So it's ft2 cosine 30. All right, now you just want to write your equations. This is a static situation, so it becomes pretty simple. For block A, you get ft2, sum of the forces in the x, sum of the forces in the y, equals 0. All right, here I can solve this. I just sort of label all my knowns and unknowns. These things are unknown. ft2 is unknown. ft1, is that unknown? No, we do know ft1 now, so ft1 is not unknown. It's a known value. And I also know fwa, do I not? No, I'm looking for fwa. So fwa is an unknown. We're looking for the maximum weight of that block that can make this situation stable. All right, so all I have to do here now is solve for ft2, and then I can plug it in to the second equation and solve for fwa, and then we're done. I'll go ahead and do that, and then I want to show you another way to solve it, which you'll get some extra credit on the exam if you do it this way. So first, I solve for ft2. Yeah, Sydney? Right, yeah, so we didn't write that actually, but here I know that ft1 is equal to fs, which is equal to 4 newtons. You know, guys, sometimes when you're solving these problems, you might just write all of your equations, and if you have two bodies, that means you're going to have 4 equations before you even think about what it is that you're looking for. And then you can go back and say, well, this is what I'm looking for, so I'll approach this problem in this way in solving it. All right, so ft1 is 4 newtons. So here I can solve for ft2. So FT2 is 4 over 0.86. That's going to be 4.6 newtons. And then plugging that in here, I can solve for FWA. I'm just going to give you the value here. I'm just plugging it into this equation and then solving for FWA. So FWA will equal FT2 sine 30, which is going to be 2.3 newtons. Well, heck, I'll just go and write it out. 4.6 sine of 30 equals 2.3 newtons. And then that's the answer. That was a pretty simple system of equations. I didn't have to plug one into the other in order to solve it, though you could see a problem where you do, and we'll work some later. Now, I want to show you a way that you can solve this, and if you do this, it's called solving this by Gaussian elimination. Let's see, if you've had linear algebra, you will have done this. You might have done this in some of your other classes. Anybody ever heard of this Gaussian elimination? No. Or if you've had numerical methods, which, if you're planning to go to graduate school, that was by far the most useful class that I ever used, as I was a physics major, but it was similar to a chemistry major. By far the most useful class was numerical methods. And what it does is they teach you how to program and solve certain systems, like solving differential equations, doing integrals numerically, doing derivatives numerically, solving systems of equations like this numerically. It's just very useful. It's really the only thing that I used as an undergrad when I went into graduate school. So if you're thinking about graduate school, like a professional graduate school, not med school or whatever, but a chemistry degree or engineering grad school, it's a very useful class. They offer it here at Nichols. All right, so I want to solve this by Gaussian elimination. And again, this is only for extra credit. I'll probably give you 5 points extra credit if you can solve it this way on the test. So if you have time on the test, that is that you've done everything else well, then you can come back and solve the system like this. First, you want to set up your equations like this. Sine 30 FT2 minus FWA equals 0. And then cosine 30 FT2 plus 0 FWA equals 4. So notice that I've just put them so that I have my variables all in a column like this. In this second equation, which is from here, the second equation is here, this equation is here. In that second equation, I didn't have an FWA, so I just put it in as 0 times FWA. Then I can write this as a matrix, just taking the coefficients for each variable and putting them in. So I have 0.5, -1, 0.87, 0. This is called an augmented matrix, and this is the augment. This is an augmented matrix. You don't need to know that word, but it just means that you have that extra thing over there. It's not gosh, what's it called when it's symmetrical? I don't remember. Anyway, it's an augmented matrix. What I want to do is get this matrix into this form. This is called an identity matrix. I want to get it into that form, and then whatever is in the augment will tell me what the answer to FT2 and FWA are. Now, I can manipulate this matrix in some ways. I can switch rows. That means like I can take one row and switch it with another row, just switch their places. So I can switch rows. Let's see, I can multiply a row or divide a row by a constant value. So for example, I could take row 1 and divide it by 2. And then that would be 0.25, -1/2, 0 in row 1. Just divide every number by 2. Or I can multiply every number by 2. So I'd have 1, -2, 0. And then I can also replace a row with that row plus another row. So for example, I could take row 2 and replace it with row 2 plus row 1, for example. Let me show you how these rules play out. It's kind of fun, actually, to solve these matrices. And you might look at this and say, well, this is completely useless, right? Because why would I want to solve this system of equations, which is really simple to solve anyway, with this really complicated way of dealing with matrices? But the reason that it's useful is while this is a simple 2 by 2 matrix, if you have 10 equations, or you have 1,000 equations, or you have 1,000,000,000 equations, then you obviously can't solve that system of equations with substitution. But it is very easy, on the other hand, to program these rules into an algorithm. You know, you take numerical methods and you learn about that algorithm and you learn how to code it in whatever programming language you use, and then solve for each of those variables. And people do that, right? Like if they consider gases and how the molecules move around, they'll take each molecule and they'll say, well, this is the equation that describes the motion of this molecule. And then they'll take the next molecule and say, this is the equation that describes the motion of this molecule. And then you have 1,000,000,000 equations, and you have a computer that can do like 1,000,000,000 calculations a second, and boom, you have your answers for the position and the velocity and the forces that act on every single molecule. So it's a very useful thing to know how to do, even though in this case, this doesn't really give us much. It doesn't really save us much time. All right, so I have this matrix. First step I'm going to do is I'm just going to divide row 2 by 0.07. Because then that's going to give me a 1 and a 0. So it's going to look like this. I'll have 0.5, negative 1, 0. I have 0.87 divided by 0.87, so that's 1. 0 divided by 0.87, which is 0. And then 4 divided by 0.87 is 4.6. So I divided row 2 by 0.87. Now I can switch row 2 and row 1. So I have 1, 0, 4.6. And then I have 0.5, negative 1, 0. The reason I'm doing that, remember, is I'm trying to get to this identity matrix. So now I'm almost there. I'm halfway done. I have my first row that matches the first row in the identity matrix. Now, let's see. The next thing I could do, and you might do this slightly different than I would. I can replace row 2 with row 2 minus twice row 1. Let me show you. So I'm going to replace row 2. Now row 2 will become row 2 minus twice row 1. Or no, I'm not, sorry, not twice, but half row 1. Is that right? Yeah, so see, I'm trying to get this 0.5 to go to 0. If I do 0.5 minus half of 1, then that'll make this point 0. I do negative 1 minus half of 0, we'll just leave negative 1. And if I do 0 minus half of 4.6, that'll give me negative 2.3. So I get 1, 0, 4.6, that remains the same. I get 0, negative 1, negative 2.3. And then the final step is just to take the negative of row 2. And so I get 1, 0, 0, 1, 4.6, 2.3. All right, let's see, what were our answers? What this tells us is the coefficient that's here, that was our FT2, is equal to 4.6, so this is FT2. The coefficient that was here, which was FWA, that tells us this is FWA. Does that jive with what we found? FWA is 2.3 and FT2 is 4.6. All right, we'll do that as extra credit. It'll be on one of the questions. I'll just have a sentence. It'll say something like this, extra credit if you solve by Gaussian elimination. You don't have to do it, but if you want to spend 20 minutes learning it, I think it's 20 minutes, right? That should be enough to learn it. Just put in your equations in. The matrices won't be terribly difficult. You might even have to put in a 0 placeholder, which makes it a lot easier. You might have a 2x2 with all four non-zero, but you can still do that in about 4 to 6 steps. Okay, this is kind of fun. This is sort of like Sudoku. Y'all like Sudoku? It's just sort of manipulating numbers. It's sort of like something you do. In fact, I think they should do this like in the Sunday newspaper. Okay. Gaussian elimination, this is called. Sometimes I think they call it like inverting matrices or something. I forget. It's been a long time since I've had it. But it's a very useful thing to know how to do mathematically so that you can apply it to lots of equations, billions of equations. And lots of people do this sort of technique when they do modeling of complicated systems. Engineers, chemists, physicists, all sorts of things. All right. Um, let's do a few clicker questions before we end the class. So we'll just do these last, do a few of these. Have we started chapter 4 yet on these? We have, haven't we? 3, what? Oh, well, that was chapter 3. Did we finish chapter 3? We did this one? Okay, we're going to wrap this up then. A projectile is launched from the ground at an angle of 30 degrees. At what point in the trajectory does this projectile have the least speed? So it's launched, follows a path like that. Where does it have its least speed, the least amount of speed? All right, I'll stop at 45, 45. All right, B is right. At the highest point, remember what the velocity vectors do. The Vy gets smaller with time until at the top it's 0, but Vx remains the same. And so at the top, you only have Vx. Which of these punts has the longest hang time? Let 1 be A, 2 be B, 3 be C. Which has the longest hang time? All right, I'm going to stop at 32. 32. Okay, we're sort of all over the board, but D is the right answer because remember, guys, what governs the time that it's in the air? What motion? The X or the Y motion? The Y motion. So if you have the same height on all of these, that means that they're in the air the same amount of time. So D is the right answer here. They all have the same hang time because they all go to the same height. A battleship simultaneously fires 2 shells at 2 submarines. They're given the same initial velocity. Which submarine gets hit first? A, B, or do they both get hit at the same time? Stop at 35. 35. All right, B is the right answer. B gets hit first because it spends less time in the air because the Y motion is shorter. Its maximum height is less, so we know that it spends less time in the air. For cannonball on Earth, the cannonball would follow path 2. Instead, it was on the moon, where G is 1/6 of the normal value, which path would it take? A, B, C, or D? Letting 1, 2, 3, 4 be A, B, C, D. All right, I'll stop at 40 seconds. 40. Okay, awesome. D is the right answer. It accelerates in the y direction at a lower rate. That means it takes longer for it to fall down, which gives it time to go out at a further distance. So it falls at a lesser rate, meaning that it's able to travel a further distance in the x direction. Spring-loaded gun. Which angle will give the greatest distance, the greatest range? I'm going to stop at 20, 20. Okay, very good. It is 45 degrees. We talked about that early on. That gives you maximum range. All right, we'll make this our last one. You're trying to hit a friend with a water balloon. He's sitting in the window room directly across the street. You aim straight at him and shoot. Just when you shoot, he falls out of the window. So you're shooting a water balloon at him. You shoot it in that direction. He's right here. But as soon as you shoot, he starts falling out of the window. What happens there? No, y'all got to go. Just about 10 more seconds. Stop at 35. We're done. All right, A is the right answer. They both fall at the same rate, so he falls, but this thing falls at the same rate, and they meet down there. And then we're not going to do this next one, but if you want to mark it, it is also A. Yes, it hits. That's the last one. Listen, we'll look at some of those concept test questions next time, and we'll work through another couple of questions like you might see on the test. We'll have a help session on Tuesday at 2. Y'all have a great day, okay?